really happy to see that many of you at that time of the year. Well, it's time of vacation, but I'm really glad you came here. And so, as I said, it's our fifth event of Cracow Robotics and AI Group meetup. And today, we will have actually three speakers. First we'll be talking Maciek Stępień. He's gonna tell us about building a low-cost autonomous personal robot. And yeah, Maciek is here. He's gonna be here in a second, like talking about his amazing project. He spent lots of time and effort on this one, and it's really worth listening. Then we will have a short break for a beer, for a little bit of networking. Later, there's gonna be Tomasz Wrona telling us about stable diffusion and $10. It's gonna be more on the machine learning, and well, you will see. It's machine learning. It's always gonna be interesting. The next one and our last speaker is gonna be Maciek Aleksandrowicz, and he's gonna be talking about latest trends in robotics. And this is gonna be a brief summary of what's going on in the world of robotics, in the big world of the papers, and what was happening on the ICRA 2023 conference in London. In the end, we'll have a short networking break, and just to chill and talk with each other with a beer. Here, if you're interested, there are QR codes for our Discord group, which is Post-Robotics, and the other one is for our meetup, so you will stay informed on what's going on and if next events are gonna take place. I'm just gonna move aside for a moment so you will be able to take pictures. Yeah, sure. Maciek, sąsiad. Okay, so seems like everyone who's interested took the picture. Okay, and now short few words about our sponsors. First of all, Codeta and their space Techies. We're here in Techies, and Codeta is great sponsor. We have partially beer is from them. The first beer is on them, and also basically the whole setup is thanks to them. So just a short round of applause for them. And the next sponsor is Huzarion. The second beer is going to be, if you at the bar say Huzarion, that you're gonna get the second beer. It's obviously limited amount, but still you get the second beer from them. And once again, a round of applause for them as well. And also, wait. Okay, yeah, and short present now after me. No, now presentation from Codeta. So sorry, I forgot your name.
Hello, my name is Jakub. Welcome in Techie Space. This place is run and created and run by IT company from Poland, Codeta. Codeta starts in 2010, and we have office here in this building. And right now we finish about 120 projects for the client around the world. And in this place we have a lot of meetups, and I hope you have great time here and another time with us. Thank you and enjoy your meetup.
And that's gonna be it for the introduction. And just give us like 2 minutes to switch HDMI, and the microphone will go to Maciek. So just a warm applause, just applause to warm him up, and stay tuned. Just 2 minutes, you know.
Mój jest mikro. Okej. Dobra, no to jestem. Tak, dobra. Tak, dobra. To możemy notować. Okay. Okay. So hello everyone. My name is Maciej, and yeah, I'm going to present the robot that I built today. Okay. So first I wanted to start with showing you the video of the finished product so that you will know what I will talk about today. Yeah. So here we go. So first the robot, it is an application of robot delivering a battle to the user. So first the robot drives up to the table, you can see. Yes, and now it will detect the battle, plan the trajectory to grab a battle, and he will grab a battle. Okay, and now with the battle, it will return to the user. It's maybe not that interesting, so I will just skip this part and move forward with the presentation. Not like this. It is really difficult to give a presentation. Like, yeah, okay. Okay, so next, wait, there's one missing slide. Okay, so here is a brief agenda of today's presentation. First, I would like to introduce the platform, so the construction of the robot and the electronics, and then I will talk about the software that you see that the robot was able to pick up the battle and give it to the user. So, okay, to give a bit of a background, the main inspiration behind this project for me was a PR2 robot. You may recognize it because it was built by a Willow Garage, and alongside the robot operating system was developed. And every time you open up an RV's window, there is a PR2. So yeah, you may recognize it. And actually, I had the idea for this project quite some time ago. And here you can see the first iteration that I did. But yeah, it was kind of bad actually, because I started it before I was in the high school, so I was quite young, and the problem was really, really hard. So it didn't really work, but gave me some experience. And yeah, then 8 years later, I returned to this project and did it better this time. Okay, so let's start with a brief introduction how the project looks like. So the main thing that I wanted to do, like PR2 was my inspiration, but it was really, really expensive. Like at the time when it was possible to buy it, it costed around $400,000. So I wanted to make it cheaper, really cheap. So yeah, I think that this part I did quite well because it is cheap for this type of construction. It is about 130 centimeters high, so about this, and the height allows the robot to manipulate the objects around the table's height. And the width and length of the robot was selected, so the robot will be able to pass through the most door frames. Yeah, and it weighs 16 kilos, so it is also quite light. It has a 5 degrees of freedom arm and differential drive base, which I will describe in a moment. Okay, so whole construction was designed in the Fusion 360 CAD software. The main components were the aluminum tubes and the 3D printed parts. Additionally, there were two parts that I bought, the pneumatic driven wheels, which were actually from the big carriage, and the caster wheels from the hardware store. All the 3D printing I did on my Ender 3 3D printer, and I used a cheap filament, like the cheapest option. And yeah, here I can give a tip. It was possible to do it, but I had to use a larger nozzle, like 0.8 millimeters instead of the standard 0.4. Yeah, then it was possible to use this filament without the problems. I used around 7 kilos of filament in total, but it is accounted with supports. So yeah, in the robot there's a bit less of plastic. Yeah, and on the bottom of the robot there is a place for the laptop, which is a main computational unit for this robot. Okay. Here you can see the kinematic design of the arm. It has 5 degrees of freedom, 2 in the shoulder, there's up and down and rotation, 1 in the elbow, and 2 in the wrist, also rotation, twist, and yeah, flexion. It is not the best option because the gripper operates in the 6 degrees of freedom actually. So the arm has 5 degrees of freedom, which is 1 less, which was kind of problematic when trying to control it later. Usually the manipulators have like 6 or 7 degrees of freedom. The human arm is like 7. It is approximated by 7. Okay, so I used the servos to, in the manipulator, 3 of the XYZ robot in the shoulder and in the elbow, which required the most amount of torque. In the shoulder, I additionally used the 2-to-1 reduction because the servos didn't provide the torque that it was specified to provide. It was supposed to give 20 kilograms centimeter, but it gave 10. So yeah, I added the reduction, which additionally it was nice because it was easier to mount the robot, the manipulator to the robot. Yes, and in the wrist, I used the Tower Pro MG996, and in the gripper and the twist joint of the wrist, I used the even cheaper Tower Pro. Yeah, and whole arm has payload of 200 grams around, which is like not much, but it is enough for the prototyping and testing different algorithms. So, okay. Yeah, and here you can see the electronic components that I used in the base. So the main board for the computations and communication was the STM32 dev board, commonly known as the Blue Pill. Motors that I use that enable robots to move around are taken from drill, which again isn't too good, but it was supposed to be the cheapest, so it is the cheapest. Yeah, the motors that I use have like 24 degrees of backlash, which was really difficult when trying to control it, but somehow I managed to tune the parameters. To get a feedback from the motors, I use the encoders with 400 counts per revolution, which wasn't also the best decision because in terms of the odometry feedback, the 400 counts per revolution were enough. But when you take into account the PID controller and the speed feedback from the motors, it wasn't too good, and I had to have like 25 hertz on the PID, which was enough, not the best. What more? I used the BNO055 IMU and the Cytron motor driver to drive the drill motors. And everything was powered up by the gel battery, which gave around 4 hours of the work time. Okay, and here you can see the electronic components used in the upper part of the robot, which mainly was the servos and the power converters used to power them. Additionally, there was LEDs in the eyes of the robots and the body there. Okay. So that was the construction of the robot. Now I will move on to the part, the software part. So everything was based on the ROS Melodic and Docker. And the service robot controller application can be divided into 2 parts: the navigation task and the manipulation task. The navigation has like 2 parts: the mapping and localization, that is SLAM, which was done using the RTAB map package from ROS. And the autonomous navigation was done using the MoveBase package. Apart from it, there was a manipulation task, so grabbing the battle from the table. And in this task, it was required to detect objects and robot actually, and then plan trajectory and around the table to grab the battle. Okay, so I will start with the SLAM. Data used here was odometry feedback, which was fused data from encoders and IMU, and it was done using the extended Kalman filter implementation, which was done in the robot localization package, and the point cloud and vision data from Kinect. So of course at first mapping didn't really work too well, and I can give some tips which helped me to achieve better results. So first thing was the Kinect in the robot was tilted into the ground, and like the half of the image was taken by the floor, and the floor isn't really distinct, and the visual features detected there aren't too useful for mapping. So it was just like cropping the image and using the upper half that was much more useful. And another thing was to actually reduce the range of data used from returned from Kinect, because I used 2 meters, like above that the data was quite noisy and not really useful. And RTAB map corrects the errors from odometry by detecting the loop closures, and the loop closures are detected using the visual approach, that is bag of words using SURF algorithm, that is like detecting features on the image. In short. I couldn't leave the mapping running all the time because there was a lot of data generated. Like, for example, this is the map of my house, and it takes like around 150 megabytes of data. So yeah, there's a lot of data. So instead, I only drive the robot around for a short amount of time, created the map, and then switched the AirTab map to the localization mode, which then was used in the autonomous navigation. Okay, and yeah, actually the map created by the AirTab map is a 3D map, and MoveBase later uses only a 2 dimensions. So the map, original map created in 3 dimensions has to be converted into 2 dimensions. And it is done by removing the floor points, by actually checking like what height it is supposed to be. And everything above that is projected on the 2D as the obstacle. And here on the map, you can see that black points are the obstacles, white points are free points where the robot can move, and gray points are not visited area. Okay, so now we'll move to the global planning. So before the global planning, robot has to know where it is supposed to go, meaning like the point where it is supposed to travel. That is the table point where the battle is located, and the user point where it returns with the battle. And these points actually were manually marked and saved before the application. Yes, and in the global planning, the global cost map is used. As you can probably see, the global cost map is based on the map that was projected earlier. Yeah, in the cyan color is the obstacles, just as before. The magenta color is the obstacles. Cyan color is the places where robots will for sure be in collision with obstacles. And all other points represent the inflated weights from highest, which are nearest the obstacles to furthest. Yes, and then using the cost map, the global planner finds the path from the current robot position to the desired position. And it was done using the Dijkstra algorithm. Okay, so next we've got local planning. And here we have, similarly to the previous step, it was global cost map. Here is the local cost map. And local cost map has obstacles, has marked obstacles, again from the static map that was created earlier. But additionally, it has the current data from Kinect also marked there. You can see here like the white box cells. They are then projected onto the plane and used later in local planning. Local planner is kind of controller. Like it takes the global plan that was planned earlier and calculates the commands for the motors that are later sent to the robot. And here I use the tab TEB local planner. It is optimization based, takes into account dynamics of the robot, so the maximum acceleration, velocity, linear, both linear and angular. And also takes into account distance from obstacles and distance from global plan. And you can tune it by using a different weight. It is quite nice planner because it can plan quite complex movements. As you can see here, the robot was in front of the table, and it first had to back up a little bit from the table, and later it could move forward along the global plan. And yeah, here you can see the planned path. Yes, and I was able to achieve accuracy of around 3.5 centimeters and 5 degrees, which was enough to move to the table so that the robot was able to grab the battle, because it had to be quite accurate. Okay. Yeah. So that was all for the autonomous navigation, and now I will talk about the manipulation. So for the manipulation, I used the second Kinect sensor, which this time wasn't mounted on the robot, but it was mounted above the table. And it is this way because the Kinect is quite large, and there wasn't enough space on the robot to mount it. Like, it was possible, but it would look kind of funny. And yeah, in the head also there wasn't enough space. So I decided to mount it above, which gave additional problems, but yeah, it was interesting. I actually had enough room for the Intel RealSense camera, which I also planned like mountings there, but decided to go with the Kinect because yeah, I wanted to do it as cheap as possible. So Kinect it was. Yes, and to detect the position of the robot, because the camera isn't mounted on the robot this time, I used the IR tags mounted on the shoulder of the robot. Yeah, and additionally, there was necessary to detect the battle, so that robot will be able to grab it, and the table, because robot has to not move into the table. Yeah, and later the trajectory planning and execution was done by MoveIt. Okay, so first detection. So for the R tag detection, there is a nice ROS package, R-Track Alvar. And here it wasn't that obvious to do it. Like first I used a single R tag, and the results weren't too good. Like you could see in the video that still it isn't the best. The point cloud is quite shaky, but now it is enough. Yeah, but with the single R tag, it was much worse. Yeah, so the one assumption that I did is that the R tags are mounted in parallel to the Kinect above the table, because the roll and pitch angles estimation when it is close to parallel is really difficult on the R tags. Yeah, and with the second R tag, it is easier to detect the yaw angle. Yeah, so I used a bundle of 2 R tags. Yes, and to detect the battle, I did some analysis on the point cloud returned from the Kinect. It was actually quite simple. I only detected, first I detected the table by fitting the plane, like largest plane on the image, and then I selected only objects on the table, having the table plane. Yeah, and then I selected the group of points that was closest to the robot. So actually, robot will grab the closest things, but I like to keep my table clean, so there's only a button. Yes. Okay, so here you can see the setup of the movie scene. So as you probably know, it is possible to add directly point cloud from Kinect to move it, and it filters the robot away from it. And it could be used to add the table as an obstacle, so the robot will move around it. But it isn't really possible to add a safety margin. So depending on how the voxels were detected, the robots could move quite close to the table, which I really didn't like. So instead, I decided to manually detect the table, which I was already doing, and I added this table directly to the move it with the safety margins. Yeah, and additionally, also the battle was added to the move it scene, so the robot will not knock it out or something; it will just grab it. Okay, and now the move it setup. So actually, move it is quite kind of similar to MoveBase. It is also a framework, but for the manipulation. Yes, and it also does kind of planning because there is a table, and the robot has to plan the trajectory so it will move around the table to grab the battle, not directly to it because it will hit the table. Yes, and here I use the Open Motion Planning library, which planned the trajectory. And additionally, it was necessary to have some kind of inverse kinematic solver that translates the position of the gripper to the position of the joints. And it wasn't that easy because I have the 5 degrees of freedom in the manipulator. The default inverse kinematic solver in MoveIt didn't return the best results. So instead, I found the BioIK inverse kinematic solver, which combines the gradient optimization and genetic and particle farm optimization. It doesn't always return the correct solution. Like it sometimes can return the closest solution, but it was good enough in my case. Okay, so that was everything about the manipulation. I also wanted to show you the simulation that I created alongside this project. It helped me in development, and also I use it now to run the tests on the software. Like I have on the GitHub, I have an action with the simulation, so it runs and ensures that I don't break anything that was already working when I add new features. Yes, and actually, all this project is open source and simulation as well. And I created a Docker with the simulation, so running it is really easy. And it is necessary to run like one command, which you can clone from the repo. Okay, so now I have again the same video. Yes, and I hope that now you will understand what is going on, understand more about it than before. So yeah, you can see the white voxels changing because these are like the current points detected by Kinect. Yes, and here you can see that the robot plans the trajectory around the table. Yes, and here it first because it was close to the table, it has to first back up, turn around, and now it will go forward alongside the global plan. Here it goes. Yeah. And it delivered the button. Okay, so that's all for the presentation. Here you can find. Thank you. Yeah, so first link is the GitHub repo with all the code, as I mentioned earlier. It is open source, and yeah, you can play around with the simulation because you don't have the robot. Yeah, the second link is my page with where this project is described. Actually, it was my master's thesis, so there is also a master's thesis link on my page, and there is much more about this project if you're interested there. Yeah, and there are also some other projects. So yeah, if you're interested, here is my page, and yeah, LinkedIn and other stuff. If you're interested, I post rarely. Maybe I will post more in the future. Yes, okay. So that's all. And questions now. Yes, okay.
Can you please give us some words about what development steps you get from the first plan, or what was the first plan until the end of the project, or some kind of milestones? Or...
Okay. Yeah. So apart from the first construction, which wasn't really good, the second construction also it isn't like the first iteration actually, because all the 3D printed parts, actually, it is a second iteration of them. Because in this project, it was quite easy to subdivide it into two problems. There was the autonomous navigation and the manipulation. So first I created the base. Yeah, I used all the motors and everything, the first iteration of the parts. Yeah, and I saw that it didn't perform too well. I didn't use IMU at first, so yeah, I noticed that I have to use the IMU to get the better results. Yes, and it was similar for the arm, the manipulation. I also started with the initial concept and yeah, noticed that it wasn't working too well, and then I created the second iteration. And alongside it, I also was simultaneously working on software to know better how I have to improve the hardware solution. So yeah, it was like the iteration over the navigation and manipulation, but more in separate ways. And in the end, I combined it. Yeah. Okay.
Some question. Maybe show the picture with the processor. Step.
Process microcontroller, yeah.
Так,
Yeah.
what the language you have? Oh, just a moment.
Yeah, here. Here
This
it
one is
is.
Arduino. Yeah. Yeah.
Yeah.
Freeze. This is freezing. This is picture from freezing.
Yeah. It is freezing. Yeah. It
This
is
is
pretty
STM.
freezing. Yes, it is possible to program it with.
This is simplest processor. Maybe
Yeah.
simplest. It is about how much is memory?
Oh, memory. I don't remember. It was,
32, maybe 32 kilobyte. 32 kilobytes in this processor. In what language are you programming?
C and Arduino.
C? No, not Arduino. It's 32, not Arduino.
It is
Arduino
possible
C++.
actually. It is actually possible to program this with Arduino. So like,
No.
I
No,
programmed like the.
library for Arduino for this processor.
There is.
Just excuse me. This is what's the driver you have?
Citron.
What's?
Citron driver.
I don't know this driver.
It is like basically it's age bridge only.
Next question. You show motor. Next picture, please.
Motors are here.
No,
You
no,
mean
no, no,
servos?
Servo.
Yeah.
What kinds of servo? What kinds of servo?
Yeah, here
Digital
three
servo.
digitals, three
Very
analogs.
digital.
Yeah, like there wasn't the picture of them, so the free
What
thing that
language you programming?
this was in Arduino.
No.
Yes. Okay.
So when it comes to the gripper, right?
Yeah.
The gripper also you fabricated with your 3D printer, right?
Yes, right.
And this motor was a plastic motor, yeah?
Yeah.
So did you experiment with some other material? For example, like if it was a glass motor, then?
Yeah, with glass it will be kind of difficult because the 200 grams. I actually added the like some soft material to the fingers of the robot, so it actually when it grabbed it could. Yes, yes, and with the glass it will be the problem because the manipulator has like 200 grams maximum payload. So yeah, glass battle could be more, I think. This was empty actually, but yeah, I also have the like video where the robot pours a bit of water, but it is only a bit because yeah, there isn't much payload.
Open motion library, right?
Yeah.
Did you use the particle swarm or the genetic one?
It wasn't the OMPL. The inverse kinematics was the one. Yeah, it wasn't like the open motion library was more for the trajectory generation, and yeah, mm, I think the distance, but like not only distance because the angles also were taken into account. So I think that distance and angles, but I'm not an expert in this library. Like, yeah, you can use it without knowing what is going on behind. So yeah, I would recommend to just check out this the BioIK library for details. Yeah. Okay.
So the arm has 1 degree of freedom.
Yes, correct.
And the grip box is 6 degree of freedom.
Yes.
Another.
Yes. Yeah, the gripper is the 6 degree of freedom, but yeah, I prefer to specify that the arm has the 5 degrees of freedom and the gripper is additional because like I don't like the where you when you include the gripper. Yep.
Local planning and manipulation. So
Yes.
I think
Sure.
that the local planning wants only on the beginning and end, or whenever you
Whenever, yeah, it is more like a split, not between the global, local, and manipulation. It is more of the autonomous navigation and manipulation. And autonomous navigation has like the global plan, which actually runs one time, and the global plan runs constantly because it has time horizon. Actually, not time horizon, distance horizon of around 1.8 meters, and yeah, it plans only 1.8 meters ahead. Yes. Yeah. There's also the actual current data from Kinect taken into account. So if you, for example, step in front of the robot, the local planning is running constantly, so it will stop the robot or plan the trajectory around you.
the global plan has not in 2 degrees of freedom or 3. So you can have only position, or you have position and angle.
Only position. It is only position, and yeah, it is like the global plan doesn't have too much information. The local planner then makes sense of it. So yeah, it is only XY points. Yeah. Okay. Thank you. All right.
Right? I mean, the bottle of water.
Yes, correct.
Correct. So the second question would be, can you tell me more or less, without precision on that side, how much time would it take you, for instance, to reprogram it to grab some another type of light stuff? You have nothing possible.
Nice stuff. It will. I mean, like depends.
How is it?
Depends on the object actually, because like as I mentioned, I actually used I actually just detect the table and detect the point of the object that is closest to the robot. So if you put some other object there, it is possible that it will grab it, but yeah, it also like has not much of the width of the grip, so it has to be also quite a narrow object. You will be able, and also the 5 degrees of freedom is limitation how it can grab it. So yeah, like if you put in like some snack or whatever, and the robot won't be really able to grab it from above. But
Could you wait with discussion like 5 more minutes or so? So Maciek will finish, and we're gonna have a short break. Okay? No, not yet, not yet, not yet. Maciek is still speaking. Like, if you just could wait a sec, so everyone will be able to hear him. Okay? Thank you.
okay, so question, yeah. I'm taking a break from this project actually. I have to go there. Sorry. Yeah, I thought about making another version better, but now I want to learn more about the dynamics. So I recently created an inverted pendulum, and I will go more into this direction. And this maybe someday.
How did you realize the communication between the microcontrollers and the
Laptop.
yeah, this camera, the 3D camera?
The 3D. Okay. So there is a laptop placed in the base of the robot, and the microcontroller is connected through the FTDI through the USB to the laptop, and camera is also connected to the laptop. Protocol. My microcontroller is serial protocol, but yeah, like. Yeah, it could be better, but not much data, so doesn't matter that much.
You have converted 12 volt to 12 volt. What is me?
The battery doesn't have really 12 volts. Like it goes from the 13 volts to like 11.5. So the 12 volts converter keeps the 12 volts steady. Yeah, like battery doesn't have steady 12 volts. It goes from. No, it goes.
So you have stable 20 volts when the battery rises down. So
Lead acid battery is very good, more better than lead polymer, lead iron.
yes.
For need, you convert that 12 to 12 volt. It is electricity.
You mean battery can discharge and get longer than 12?
Yes, that is correct.
I saw the student. It's no need. It's very, especially China's converter. This is a China converter.
Yeah,
This is China server. China server, 5 volt. 5 volt. 6 volt. 6,
Yes.
6. For what?
For servo.
This is electricity. This is not program.
Yes.
Programming especially. Next question, maybe. Not a big-
Next question. Sorry. Sorry.
Beautiful work.
Thank you very much. Question.
Why do you use extra algorithm instead of base?
That is the really good question. There is, I think, something wrong with the heuristic in the implementation in the ROS because it performs worse. And yeah, like the computation time, it won't matter much. Like it is a really short path. So yeah, like as far as I remember, because like I was doing this 1.5 years ago, so I don't remember all the details, but it wasn't that smooth. Like it has some strange things going on like this. So yeah, that's why the extra.
You don't say about the sensors.
Yeah, sensors are Kinect sensor.
But
What?
have you sensor? Is a crash?
No, there is no sensor in the gripper.
It's very simple because 5 volt.
Yeah, yeah.
5 volt about 1 ampere within cat watt. It's very simple.
Yes, probably.
Simple destination. Why don't have any dark?
Because it is expensive.
That is not Arduino.
You mean LiDAR?
But it's very
Right?
beautiful.
Yeah.
Demonstration.
Okay, thank you.
Thank you.
Maybe a simple stupid question about how do you implement the movement of the drill motors using encoders, how they are physically mounted, and whether you have the reference point of the drill motor.
The encoders are mounted using a timing belt. Like there is an axle going from the drill motors that is rotating, mounted.
Linear mounted encoder, and then
No, it is not linear mounted. There's an axle that goes from drill motors to the wheels, and there is like a gear here, and there is a timing belt connected to the encoder that rotates it. Here it rotates, and here it rotates the encoder. Yes, I have an encoder. Because it was on the previous slide.
This is very strongly task.
Yeah, here is two big encoders. See? Yeah, here. 1, 2.
And corner is a circle with 1 diode and next photodiode. And
It is everything is inside the encoder. Yeah, it is like the optical incremental encoders, and everything is packed inside here. Yes.
I have a question about software.
Okay.
You show us the proper image that you show us on the slide about when you use Docker Compose. That was the whole application, or only example, or
It was actually the run everything. Like it runs simulation, and it runs navigation stack and manipulation stack also. There is actually another command that you have to send to make the robot go to the table and deliver the battle. You have to just like trigger the whole software stack to execute the action. Thank you.
What have you learned, and what would you do differently?
Oof, that is like another presentation. I think like I would do everything differently. Like, yeah, I'm proud of this project, but yeah, it's kind of bad. Could be better. Like, you want specifics?
The main thing that you like, for example, like when you made the first assumptions about the project, what different assumptions did you make?
Don't make it as cheap as possible.
That's what I was saying. Yes.
I mean,
that was the worst constraint you could imagine.
Yes, but now I have a job. Now I could do better robot, but yeah, then I didn't have a job. So I'm kind of proud of this assumption. I think that I managed to do the as cheap as possible robot, and yeah, I think that I managed to achieve this. But yeah, now I'm older. I would prefer to make something more reliable and just better. And I don't think that I would be possible.
Do you think that rapid prototyping techniques like 3D printing are really scalable in this situation, where the PLA is not really a material that can withstand more than 200 grams of torque I mean, it can.
It wasn't really a problem of the PLI of the material.
Okay,
so I don't think. I'm not sure if it will be durable in time, like and weather.
So it's good to prototype, but not really good for production.
I mean, for production, depending on the scale, I think up to some point maybe. But yeah, this project is nice, but it isn't scalable. It isn't possible to do more of this. It takes too much time. Yeah, there are better production techniques for scaling. Yeah, but like I think that it depends on the how large would you like to scale.
Think about Raspberry Pi.
Yeah, I used Raspberry
Future
Pi.
Raspberry Pi.
Yeah, I used Raspberry Pi.
You bet.
Yeah, I didn't have. I don't have the schematics of the connection of PC and the Raspberry Pi. I used the Raspberry Pi, but it was more of the convenience. Like everything that I did on Raspberry Pi could be connected to the laptop, but it was more convenient to use the Raspberry Pi, so that's why I use it. But yeah, I could use laptop instead. Yeah, I didn't say here about many things because there is like a lot. I say that I have like the master thesis written on it, and there are I think all the details. I hope that there are all the details. But yeah, it was difficult to fit everything into a 1 hour presentation.
And okay, now we're running out of time.
Yeah.
Sorry, Maciek, it was.
Okay.
I'm just gonna move a little bit. Yeah.
Well,
Okay,
okay, let's go.
Maciek to Maciek question.
You have created a wonderful robot. And
Thank
you
you.
got many steps to accomplish it. And after all it, I have one question. How often those robots bring you a beer?
Yeah, like it takes more time to set up it than to grab a beer myself. So like none. So if you would like to bring the beer, I recommend other ways.
Okay, thank you very much.
Thank you. Thank you.
So yeah, the last question was definitely worth it. And so now we're gonna have a short break for a beer and for networking. It's gonna last till 8 p.m. So we will just switch some stuff with laptops here. Don't worry. Just take your time and talk with each other. Just for the information, we're gonna make the break longer for like 5 minutes, so everyone will get their beer. So we're just gonna sit there quietly and listen for the next amazing presentation. Thank you. Can I get your can I get your attention for a sec? So if you could slowly move towards the tables, because our next speaker will start soon presenting. His name is Tomasz Wrona. he will talk about, well, we're gonna just slightly drift away from the robotics into image generation. It's gonna be a little bit more general topic, but we have AI in the name of the group, and the display went off for some reason. Um, ah. Anyway, so the image is gonna be back. Oh yeah, it's already back. It is. It is. Anyway, we're gonna drift away a little bit away from the robotics, but we have the AI in the name of the group, so yeah, it's totally fine. He's gonna talk about the image generation, basically, like as the name of his presentation says, it's gonna be stable diffusion and $10. Now let's just give him applause. And Tomek, the microphone is yours.
All right, now, cool. So in the meantime, while you're still there, and the presentation is not working again. All right, so there is a small task here. Who could spot the real logo of this meetup group? Like, I can give you a little tip that is tricky here due to the how the display is, like the screen is being displayed. No ideas, right? It's here. Anyway, yeah, so about me. I'm Tomasz Wrona. I'm currently working as machine learning research engineer at Let's Enhance. Let's Enhance provides the image enhancement and image generation solutions. But before that, I worked 2 years as machine learning engineer and tech lead at Global App Testing. Will do. Well, actually, I'm speaking the same amount of noise. I'm on the same. Never mind. All right. So yeah, at Global App Testing, I'm working mostly with reinforcement learning and testing autonomous web applications. Before that, I worked at Aptiv for 4 years. I started with as computer vision engineer. Then I moved to reinforcement learning, and I was working on autonomous driving stack. And I hold Master of Science from AGH UST. So the agenda for today is straightforward. I will introduce you shortly to the diffusion models in general, and then we'll talk about what stable diffusion is, what's this mystery of stable diffusion, what it actually is. And then we'll walk through some major advancements since the release, because stable diffusion has now more or less a year. And there were a lot of stuff released in this last year, some of them about tooling. So I will show you the most popular user interface for stable diffusion, as also the most popular Python library for this from Hugging Face. And about the advancements itself, there are like 3 paths of them, 3 families of advancements that each one touches different problem with image generation. First one is about control generation. So when we want to have more impact on what's going to be generated. Another one is about subject generation. So we would like to generate something that stable diffusion didn't see before. So we would like to inject some new subjects. And finally, as those are very large models, we have the same problems as with large language models, where the models is simply biased or is not perfect. So we will also speak about aligning with human preference. Okay, and what's the mystery about $10? It's because like you don't have to buy extra expensive computer for that, because like you have to have GPU, but you don't have to like spend a lot of money for that. There are services like RunPod or Lambda Labs where you can rent a very cheap GPU instances in the cloud. There are some limitations, like for example, RunPod runs your code in the Docker container. You don't have access to the virtual machine itself. but still, like for experimentation, for small research projects, it's perfectly fine, and the prices are much lower than on AWS or GCP or Azure probably as well. And especially if you had an idea to buy one computer for yourself. So so the idea is that this presentation and even more were created with less than $10. Diffusion models. So maybe I will ask, how many of you heard about stable or diffusion models in general? Stable diffusion. And how many of you are in the machine learning world, like doing something with computer vision? Cool. So far, if you were interested in generating images with machine learning, you had two options. You either went for variational autoencoders, which are like fast, which covers the distribution well, but the problem is that like usually you don't have good high quality samples from that. They are usually like, for examples for face generations or something like where they shine. But usually if you want to cover like large image generation problem, that's not the option you go. There are GANs which solves this problem. Like you have this high quality samples and very high fidelity data. But the problem with GANs is due to the nature of how they are trained, that you have these two models, they compete with each other, and they lead to various problems in the training. And this makes them like, they don't work very well when covering a large distribution of the data, which is what we would like to cover because we would like to generate any possible image in the world, ideally. So that's where diffusion models come, which solves these two problems on the right, let's say. And originally they were very slow and it took ages to generate something, but actually it's no longer true, and we'll see that in a minute. So diffusion process consists of two types of diffusion processes. First is the forward process, where there's no machine learning here yet. You just take an image and you add a little bit of noise to it. And then you repeat it for some time. So for example, 1,000 steps. And so there's a proof for that, that if you add this a bit of noise at every step, that in the end you will end up with completely Gaussian, like completely random image consisting just of the Gaussian noise. Cool, right? But like what it gives us. So here's the bit of visualization of this happening in the image. So if we have forward process, then we probably should have also the reverse process. Sorry about that. We can always try with USB-C if you have one, but okay. Yeah, so if we have forward process, then we probably have also a reverse process. So let's imagine this process that if we have an image, and if we are able to predict what noise is visible in this image, then you can subtract this image. And then again, if we repeat now this for multiple steps, we may end up with a perfectly fine image, right? So if you have experience with machine learning, you should already have intuition where it's going. So let's treat this reverse diffusion process as a machine learning problem, and let's try to train a neural network, train a deep learning model to try to predict what noise is visible in the image. And so typically for computer vision applications, because our problem here is that for the given size of an image, we want to predict. Okay, just a second. All right, thank you. So yeah, it's typically for computer vision problems where we like to map like an input image to something of the same resolution. In computer vision, we have this well-known architecture, UNet, and let's use it right here. And let's train it in a way that it learns to predict the noise added to the image. So the model has as its input, it sees the noise image at some certain level of added noise. So it sees, for example, noise image where from like 100 step. So it's already largely destroyed, but still there is some information there. And we learned this model to predict what's noise there, and we simply compare it with the noise we added there, because we added the noise there, so we know what's the label here. And let's just do a mean squared error here, and let's optimize this model. And it turned out that it works pretty well. There's interesting fact about the noise we add. One is about like how to add noise progressively during training, but more important factor to remember is that those models are usually trained at certain resolution, and so they're trained to denoise certain amount of noise in the image. So if you train it, for example, at 512 by 512 resolution, and then try to generate the model at 1024, it might not give you good results. I mean, it will work, but you will have a lot of artifacts in the image. And that's because of the way how the image resolution relates to the amount of noise it can absorb, let's say, because in higher, as the resolution gets higher, we have this pixels redundancy. There are more pixels that could be destroyed before we lose some information. And we'll see effect of that later in the demo. So I said that we are destroying this image during training. We are destroying this image in like 1,000 steps. So does it mean that I need to run the model 1,000 times to get one image? And the answer is yes. But at the same time, the answer is no, because like it was true at the beginning. So that's why this said that diffusion models are slow. But since the original diffusion models, like 3 or 4 years ago, I don't remember the date, there were a lot of improvements. And one of them were about samplers, which allows us to speed up this process of sampling from this model by approximating this reverse process. So in the simplest case, in the simple words, we just, at every step, we remove larger amount of noise than we predict. And there are different ways how to compensate that. We removed too much noise and so on, but we won't get into details here. The important fact is that we don't have to retrain the model every time we want to use another sampler. We could have the same model trained 1 year ago and just experiment with different methods how to utilize the knowledge it possesses. Okay, so far it was about, we were working in pixel space. So we were denoising every pixel in the image. And if we go to 1024 by 1024, we have 3 million of pixels to denoise because of 3 RGB channels. So we have a solution for this in computer vision. We have these variational autoencoders, which allows us to compress the information visible in the image. So we can take the image, for example, 1024 by 1024, pass it through encoder part of variational autoencoder to get it latent representation. And then when we want to go back to the pixel space, you can use decoder of this autoencoder, and we are back in the space. How large is this compression? So usually for stable diffusion pipelines, we use variational autoencoder, which reduces spatial size, so width and height of the image by 8. So you have 64 times reduction, but we add 1 extra channel. So from 3 RGB channels, we end up with 4 latent channels. So still 64 time reduction in spatial size, but adding 1 extra channel. And yeah, so when we encode it and we are in the latent space, then we just do the same as I mentioned before, but we're doing this in latent space. So we are operating on already compressed representation of an image. So we can it allows us to do more with our models because they don't have to learn, because they outsource the compression, the redundancy of the pixels to the variational autoencoder part, which is pre-train and fixed during the training. So we just care about semantic representation of the image and how to create those semantics in the image. Here's the example of how good are those variational autoencoders for compression. Here's the image which was compressed and decompressed with this model, and you can barely see the difference. That there is some distraction, this barrier at the top of the lighthouse, but apart from that, yeah, it's very good at compressing this information. Okay, so going back to latent diffusion models, there is also one extra thing that comes with these models that were initially proposed in this paper. that we can now start conditioning our generation on something. Because so far we were using this unconditional generation where we were just modeling some distribution of images, but we now want to generate something specific. So one thing how we can do it is by introducing some conditioning on the right. And the simplest one, the most popular one, is using text as conditioning. That's what everyone knows as prompts nowadays. And we can feed it from some text encoder, text embedder, whatever. I think in the original paper here, it was like some clip-based transformer, something like that. So the embeddings are like very closely related to the image embeddings. But anyway, and then those embeddings are just injected into cross-attention layers in this unit, because now this unit is slightly bit more complex, because if you know that in the typical unit, there are just this residual connection between layers. But in this unit here, there are also cross-attention layers after every residual network. And those text embeddings can be injected there. And using cross-attention, this model that generates images can now utilize the knowledge from the text to generate something that relates to the text. It has to, because in the loss function, now we added this embedding to the model, and we expect it to generate image complying to this text we provided. So one more component before we move to the stable diffusion is, okay, to train something like that, we need a lot of data, right? And how one can come up with such large data set. And there is something called Common Crawl. It's an open source project where like the internet is being crawled all the time, and there are petabytes of data available, and mostly HTML sources of the web pages in the internet. So what the guys from this Lion Institute, I don't know how they call it, group, did, they just took this Common Crawl because it's open source, everyone can take it, and they just parse the HTML pages for image tags and source attribute, which points you to the image, but also the old attribute, which is like stands for alternative text. It's a good practice to put there description, what is in the image, right? And of course, not everyone is doing this because it's not obligatory to do that, but some do. So they just, correlated the image with the alternative description, which human provided, for example. They of course did some filtering there to filter out some inappropriate content, let's say. But still, yeah, they come up with like 5 billions of images, image text pairs, and so on. So that's a very good data set. But of course, as with all data sets of this size, there must be a lot of bias there and not very trustworthy. So finally, the stable diffusion. So unfortunately, there's no surprise here. Like stable diffusion is just the latent diffusion model I mentioned, but with some tweaks, with some like special versions of models used there, and so on, like data set used to train that, and so on. It's like a joint work of these 3 research groups, especially Stability AI is now, say, leading in this because they are releasing the largest model, with the Excel model being released. The research version 0.9 was released like a week or 2 weeks ago. The technical report, which is partially here visible, was released last week. And we are now waiting for the official release of the weights for this stable diffusion XL. They say they did a lot of improvements to that model, so I'm very excited to see what it can do. So here's some examples of what stable diffusion is capable of generating. Actually, mostly art, let's say. But let's take a look at this. So I didn't practice it doing one hand, but let's see. Okay, so let's start with, let me just see if this works for sure. Yeah. Okay, so this is the stable diffusion web UI. It's like the most popular UI to use for stable diffusion. If you don't want to go into the code or you don't want to create anything on your own, you can clone into the GitHub repository and just launch it. And it's based on this Python Gradio library, and it works pretty well. So what do we want to generate? Let's start with something very simple. Let's start with just a sheet. Let's see what it gets. not really what I had in mind. Let's start with increasing batch size. So for every image, we have 4 instances. All right. Okay. Actually, I was thinking about like the ship with sails. So let's try sailing ship. All right, we have sails. Okay, so to make it shorter, I just take the prompt I like to see how it affects the generation. So there are a lot of things that I added to this prompt. Actually, this prompt I took some from like the prompt database site. Yeah, that's much better. Like we have this mood because what have we used? We used cinematic lighting. We used trending on ArtStation, 4K, hyper-realistic, focus, extreme details, Unreal Engine. So those are like, now if you think about this, how this data set was obtained, you can see why these keywords work. Because like, for example, if in the common crowd there is like this ArtStation, I believe this is some kind of website for posting art. If they crawl this ArtStation, then probably some images there are automatically like to this alt tag. Every image is also additionally tagged with trending on ArtStation or something like that. Maybe. So, but I believe that's the way how those keywords work to make this image look into this. So like Unreal Engine, because probably there were a lot of images that were labeled under Unreal Engine. So it transferred this mood of Unreal Engine renders to this image. So we can choose one of the image we like most. For example, I don't know, this one or this one. Maybe this one. Yeah, this one is great. So currently we generated 512 by 512 resolution, right? First thing, let's try generating it at 1024 by 1024. Let's see what we can get. I will lower down the batch size because now we're generating at 4 times resolution, so it takes a lot more graphics card memory. I don't know if it can handle generating batch size of 4 images. Yeah, so that's the problem we start to see. I wanted 1 ship. I got 2 ships with a lot of sails. And that's the problem of generating at not native resolution here, because like we started with a empty, like fully noised 1024 by 1024 image. So there was a lot more noise to denoise, and this model just can't come up with a solution for that. So it starts generating artifacts. I mean, in the end, it works, right? There are 2 ships. If you look at this from the far distance, you can even believe that's the real image, but no. So how can we generate at this high resolution? If we can generate it in this way, oh, I haven't fixed the seed, so I will have a slightly different image right now. Yeah, let's go with this one. Okay, it's ugly one, but still. It's 512 by 512. It's just, I think if I press this one, yeah, it's this resolution. I would like it to make it bigger. So what can I do? Well, I can start generating at 1024 by 1024 because I end up with what you have seen. But I can generate at 512 by 512, then upsample it to higher resolution with any well-known upsampler, either like a naive way, like a Lanczos or nearest neighbor interpolation, or some GAN-based solution for upsampling. And then I can run a few more steps of the denoising loop. I can add a little bit more noise to this now large high-resolution image, and then run my denoising model to denoise this model. Now, as the image looks more or less the same, it's just there's just a little bit more noise added to the image. It can come up with a second ship or with a lot of sails. Actually, there's a lot of sails here, so it might gonna happen. But let's see, I'm adding like a 0.2 denoising strength. So I'm adding like a 20% of the image that will be consisting of a pure noise only, okay? And first I'm generating at 512, then I'm upsampling to 1024, and then I'm running this extra steps at high resolution. So the first low resolution steps are very quick, then it takes a little bit slower for the next 20 steps. Okay, I haven't fixed the seed, so that's why we have something completely different. So let's generate first again at 512 by 512. Sorry. Okay, let's reuse the seed, and now let's generate at higher resolution once again. We should have something very similar to this image, yeah, but at 4 times the resolution. Yeah, and if we see now, yeah, it's 4 times the image. But it's not only about upsampling. That's the powerful thing we have here, because what else we can do is what I did with the logo of this meetup, right? So if I take logo, and without any prompt, I ask it to add 0.2 noise to it and denoise it for 20 steps. And let's use batch size of 4 again. Because one thing is that you can start with a completely random noise, but no one prevents you from using a noised real image to start with, right? So you have 4 versions of this logo. And every time we have completely different details on the dragon. And of course, the letters are bad, but that's a well-known fact that it can generate text very well. We can go higher with the denoising strength just to see what's going on. Yeah, now it just diverged very much from the original idea, right? Yeah. Okay, let's go back to the presentation. So yeah, there are problems with just conditioning on text, right? Because like I have this imagination that I wanted a scene where there was a dog sitting on the grass on the left, a girl reading a book and sitting on a bench on the right, park in the background, sunny Sunday afternoon. So, okay, I have this, but it's not my composition. I want dog on the left, I want girls on the right, I want a bench. That's not what's happening here. So like, that's the known problem of these image generation models, that they are not well with the composition itself, right? But fortunately, we can solve this problem with ControlNet, which was released in February this year. And what it allows us to do is to additionally control the generation process on some additional input. And here, the input is only this CaniEdge output. It's just the source image, just for reference, how this CaniEdge input was calculated. But all these 4 images on the right are generated based on this sketch in the lower bottom of the screen, right? So now all those images are aligned to this condition, and so you can imagine that if I want to girl on the left, girl on the right, dog on the left, I can simply sketch it or do it in another way and have the image I wanted. And how it works? So I was previously speaking about this conditioning, and I was talking only about the text conditioning here. But of course, as in the picture itself, you can use other images to condition your image. And that's actually what Stability AI released some time ago, I think before ControlNet, where they train it on a depth model. So there's the second image is the depth estimation of the first image. And then the 3 images, the 3 next images are the images generated based on this condition. It works, right? It's pretty cool. But to train such model, you are retraining the whole model, which was trained on a large data set. So it has a lot of knowledge already there. And it's very easy to overfit such model, right? So yeah, it works, but actually we can do better. And of course, you have to retrain the whole this denoising unit, right? But the guys behind the ControlNet, I think they were from Stanford, figure out a better solution for that, which supposed to work not only with like an image generation thing, but in general neural networks work. So on the left, you have like a typical any kind of neural network block. And on the right is the trick they use in ControlNet. So you can log the original parameters, you can copy them to a trainable copy, and you can wrap it up. It's something called zero convolution, which is basically a typical convolution, but with the weights and biases initialized to zeros. So at the first iteration where the training starts, there's no impact on the output, right? Because everything is multiplied by 0. So in the end, there is nothing is being added from this branch. There's just this locked copy, which contains all the information about the images from the internet, no modifying. And this allows to just a slightly, let's say, distilling some extra knowledge to the model. And what's else is that you don't have now to fine-tune the whole unit model, because they're using this just in an encoder part of the unit, and they're injecting this through these residual connections to the decoder part of the model. So you have now more or less twice less parameters to train. And you don't have this problem with easily being overfitted. You don't have to use a large data set. They usually use something like 50,000 images or something like that. So that's not completely different scale than used to train the original model. And it's like a plug and play. You can, at any time, you can stop using ControlNet and stick to the original model and so on. And here are some results from their repository, where here is the conditioning on depth, so something that guys from Stability AI did. You can also condition on Canny edge map, on open pose, and like to, you can see the very details here that there is this elbow labeled, and this elbow is visible in every picture, right? That's great. Like just apart from the main person in the picture, of course. And there are many models. Each one allows to condition on different things, and you can combine them together. So condition on multiple control nets, and I have demo for that. Okay, so I had in mind one thing that, yeah, there's this technique. I don't know why it's called map bashing, but it's called this way, which allows you, because like one thing you can do, you can just go, for example, to text to image. Let's get rid of this, and enable ControlNet and just decide on what you want to condition. And then you just upload the reference image. So for example, that I want to condition on some Canny edge. And I can just, yeah, because I had this idea, spoiled, that I want to generate image that there is a castle somewhere in the right. There is this hypoglyph from World of Warcraft somewhere on the left. Yeah, and I wanted to have a mood of World of Warcraft render, right? So what I did is that I first go here and choose hypoglyph. And actually, it was not Canny, it was soft edge. There's a different algorithm to extract edges here. I run the preprocessor manually, and I got this image, and I saved it. Then I went to my castle image. Again, generated a soft edge image of this version. I saved it. Then I went to GIMP, very good tool. And I just combined them into something like this, okay? And that's my condition for the image. So I just spare you this waiting, and I will just upload it directly here. And now I don't want to use any preprocessor because it's already preprocessed. And let's disable this for now. Let's use random seed. And let's just, first let's start with just batch size 4, and let's just start without any prompt. Okay, there's a problem because I didn't enable the control net. So that's what's happening from Stable Diffusion when you don't use prompt at all. Perfectly valid images, right? Now it should be better. Okay, it starts. I guess there's a bug in this UI. So like the composition is okay, but like, okay, I didn't tell him to use World of Warcraft style. So let's tell him that I want World of Warcraft. It's much better, right? Especially this one. I experimented with this a bit, so I can try to use the prompt I had already experimented. And there is also option to provide negative prompt for the image. And you can imagine how does it work. It tries to be as much as possible compliant to the prompt, but as much away from the negative prompt. So if you don't want something to happen in the image, like blurriness or bad quality, I know it doesn't make sense, but you can just say that you don't want bad quality, and you won't get one. And now we are in the World of Warcraft. And again, like if I like one image, I can make it larger. I can make variations of this image and so on. So like a lot of options here. All right, so let's back here. So that was about controlling the generation. Now, what if I want to generate something that's not possible? Like, unless you are a famous person, Stable Diffusion won't generate you, right? Or like your dog, or like any item that isn't publicly available. So the guys, I think from Google, come up with this Dreambooth algorithm, which allows you to modify diffusion models to just using a few images. And here is, I think, literally 4 images of this dog used to inject the knowledge of this subject into the diffusion pipeline, and then allows you to generate images as it's some known subject to this model. How they did it, very briefly. So as they have only 3 to 5 images or 10 images, the magnitude is very low. They do it at low resolution. First of all, first you have to come up with some unique identifier for the subject. So you can't use, I don't know, word car when you are about to generate your dog, because like it will mess up the semantics of this word for this model and it won't work. You have, like in the original paper, there were a lot of talking, a lot of discussion about how to find this unique token in the representation. In the end, it doesn't really matter as long as it's unique. So something that is specific to this subject and won't be confused with something similar in the world of semantics. So yeah, going back here. So first, they're doing this in low resolution. So they're generating these images in very low resolution just to avoid overfitting here. But at the same time, they're using this prior preservation. So because I want a V dog to be this my dog, but I don't want to hard performance of this model when I want to generate a dog in general, right? So I'm using they're using the model, the logged version of the model to generate me dogs first, and then using this prior preservation loss combined with this reconstruction loss of these images, I'm fine with generating 64 by 64 images of my dog. But then, of course, I don't want my dog to be at 64 by 64. I want it, for example, to be 1024. So there is this cascading approach where they're using super resolution model at the end, and they fine-tuning it also just with those 3 or 5 images. So it's getting probably overfitted here. But it allows to like upscale this image and restore the details that are in your subject. So something that is not visible in 64 by 64 resolution, but it was visible in the original one. And there is a very short demo for that, where we use this diffusers library. Hope it's visible now. So yeah, I trained it to learn some headphones. Like I experimented some time ago with this. I'm trying to train it with my face, but it didn't work very well. Like there are some people that manage to make it work with faces, but I'm just not lucky. So I'm used just 5 images of headphones I had at home. Just some random images, right? And I train it for 3 minutes. Now I present you, I will spare you this 3 minutes. I will just show you the pre-trained model, how it's gonna work, because it got stuck here. Oh, it's working. So I'm loading this model that was fine-tuned. And yeah, there's this SKS token that That comes from the original paper. That's where the discussion was about to finding a token which is rare enough. So I just using them always, but it really doesn't matter. Take some time to load this model. And we can now run inference. So I ask for a photo of SKS headphones laying on a wooden bench, beautiful park in the background, sunny Sunday afternoon, 4K. And here they are. And here are more images like that. And the model saw only 4 or 5 images of those headphones. So yeah, pretty cool stuff. Going back and near the end, the final thing, aligning with human preference. So as the model is trained, again, on large data set, potentially unmoderated, apart from some filtering mechanism added there, it suffers from biases or just unintended outputs. So following the idea that was probably like the initial idea for ChatGPT, there was this Instruct GPT paper like 2 years ago or 3 years ago, where they had this GPT model, large language model. They asked people to demonstrate what would they like to see as the desired output for some set of prompts. And then they fine-tuned the model first with the supervised learning. Then they were labeling the answers again. They were using reinforcement learning just to fine-tune this large language model, right? So what about something similar in this world? So I would speak about 2 possible alignments. One is about this being alignment with the text you provided. So as you saw before, there is this problem that I want something on the left, something on the right. It doesn't work. So they collected a list of problems that are most frequent in those models. For example, with counting how many objects I want on the image. So for example, 2 dogs or green dog. This is regarding to the colors. And it did something similar, but without reinforcement learning. So they asked humans, like they generated a lot of images for this set of prompts, and they asked people to label which one of them are following the prompt perfectly, and then train a reward model, which they use to fine-tune the model in a supervised way. And in the end, it works very well. Like at the beginning, it had problem generating 4 tigers. In the end, it generates 4 tigers. 2 green dogs on the table, here they are. So that's one thing, how you can always fine-tune these models. I wish something like that will be present in the default model at some point. That would be great. And the second thing is about improving aesthetics, because right now, it's very likely, if you are not familiar with all the prompts, all the settings, that you have to run a lot of, generate a lot of images to find the one you like. So, okay, that's how Stable Diffusion works. Okay, we accept this fact, but what we can automatically run this process. Let's generate 100 images, but select me the most that I like. So again, I think the guys from Stability AI, they did this experiment. They hosted this public app to collect a lot of data from anyone in the internet, that they presented 2 images generated for the same prompt. And they asked to choose people, which image do you like better, or that there is no image significantly better than the other. And they managed to collect a lot of data, I think 500,000, this comparison, something like that. I don't remember the numbers. And they trained a simple model, peak score, to predict the peak score, which is like a measure of how aesthetic is this image, or how preferred is this image in comparison to other images generated by the Stable Diffusion model. So as they didn't use it to fine-tune the model, they just use it in this way that they generate 100 images and they select image based on some way. Then you have this vanilla column where they just randomly sampled an image from 100 images, and peak score column where they choose image based on this highest peak score. So as you can see, it's working very good, because like this private futuristic cabin on Mars, like this image looks pretty cool. Car made of zebra skin. In comparison to this one, it looks very cool. So like a natural next step here is to use it to fine-tune the model itself, right? So probably someone will do it at some time. Okay, so I'm also posting here some links. One cool idea is video generation from NVIDIA, I think, where, yeah, this align your latents, where they speak about how to extrapolate it further into video generation. And yeah, so I think that's it. There should be a video here. Thank you. Yep, question.
It's very impressive, right? The diffusion model because it creates images of the mapping, right? And then we can control it, so it gives us a lot of power.
Mhm.
I'm very interested in understanding like, what kind of application we can create based on this that we can monetize and like we can offer to the wider audience, right? Any thoughts on that? That would be
Yeah, the good question. So the question was how to monetize it, right? So some of you may heard about like two, let's say, competitors to this, because there is this Midjourney, which probably most of you heard about. So it's a paid service for generating images. And if there are people that are okay with paying for generating these images, this is free. If you just rent a GPU instance and you have one at your home, you can run it for free, right? For Midjourney, you have to pay. There is the DALL-E from OpenAI, and so they have customers. So there is a business here. Potential applications. So for sure, generating art and creative stuff.
For example, with Bitcoin and stuff was very, the cryptocurrency was booming. So NFT was a very viable market for this thing.
Like I didn't hear the last part.
I would say that NFT was like a pretty fertile market for this generative AI, right? I'm asking about something which the application that we use on daily basis, right? Like for example, something about a learning material, right? Like to create a video about certain concept that I want to show or something,
Exactly. So everything
Yeah.
based on some creativity, or like e-commerce, like where you have a lot of images that you want to show in your social media, for example, right? So you don't have now to take you these pictures on your own, or pay third parties for taking these pictures for you. You can just generate them on your own, however you would like this photo, right? For example, for social media or something.
Won't be 100% sure, right? Because there is a hallucination problem with the LLMs. Just can you throw some light on hallucination problem? If you have read something new.
On LLMs, I'm not in NLP usually, so yeah, I'm not really up to date. But there's similar problem here, but with this conditioning on different additional inputs, you can mostly get rid of it. And if you stick to the right resolution, you just stick to some rules, then you are fine with the images that it generates.
Sorry. Here.
Yeah.
Do we actually know what's the difference between the stable diffusion and paid solutions like Midjourney, which, well, if anybody have ever used Midjourney knows that the resolution and the controllability of the art that you can create is much higher. Like I have been trying to create the same thing in many models to see how useful they actually are for graphic designers, photographers, and the Midjourney is just the most controllable out of them all. So do we actually know what the hardware or I mean, because how the hardware is also the part of the how it works, the graphic cards, the GPUs, the RAM part, but also the software. Do we actually know what's the difference?
Short answer, no.
All right.
It's because they earn money on it, so they don't like to share any details on what's going on. But I fully agree that for the regular user, for the out-of-the-box performance, Midjourney is a way to go. Like, you don't have to set it up, right? If you are not a programmer, and you have a better quality of images with a simple prompts, because they they certainly fine-tune their models, like for the preference, because they are working on as this Discord bot, and there is option always to rate how much do you like the image that is generated. And I'm 99% sure they're using this to fine-tune their models to generate images that their users like most.
I mean, they don't use it as much as I would like it to, because they use Discord when it's actually there's not much feedback between what you actually create and what you cannot make a feedback of okay, that's what I wanted to do. But but just one more question. Because when it goes to usability of this solution, it can be either just a toy, fun, like you can just spend 2 hours, like I sometimes do, and create some funny images or maybe even videos. But when I work with the people who actually are graphic designers, what they really want is the controllability and repeatability of the solution. So when you can use, for example, one face on multiple images, or one style that is, the seed. One thing I'm struggling. Maybe you can help me with is the characteristic of the seed when you use the seed to diffuse the image. And sometimes it's actually not really helping with repeatability. Can you say something about?
So about the seed, I don't really understand.
I mean, in Midjourney, they use the pseudo, random generator to create seven
seed number.
The seed number, yeah. And out of it, you can create some image, and you can literally just create the copy of it, or create a copy of it in the same character of the image using the same seed with different prompt.
I think I understand. So yeah, with Midjourney, you have like some extra abstraction for this. Like, it's as simple as you reuse this seed to generate something similar, right? Here you can get something similar with, for example, this image-to-image approach. I showed you that I want to generate something similar. So how I do it, I just instead of starting from pure noise, I just take the image's reference, add just a bit of noise, and you can control how much noise I want. And the amount of noise you add, it controls the freedom for the model to how much new details it can add. So if you just use like 0.1 extra noise add extra noise to the image, it won't change you completely your image, right? But of course, it's hard if you want to change specific details, but you can do in painting them. So then just select a region of the image you want to change and ask model to repaint just this part of the picture and keep everything untouched, right? So it, of course, requires a lot of like extra manual work here, but it's doable. I think like the Midjourney maybe has just a better UI for that, like a better
solution.
interface.
Yeah, I get it. Thank you very much.
More questions?
Can I have one more question?
Yep.
As we know, like the other models like Midjourney or some other have struggled with some countable known elements like fingers, strings in the guitar, or hours on the clock. And this model also have the same problems.
Yeah, so it's getting better with newer version, because like the first version of Stable Diffusion was released like a year ago. It's in August, I think. And there was this 1.2, 1.3, 4, 5, then 2.0, 2.1. So with every version, it's getting a bit better. But it's still not a Midjourney performance. Like Midjourney is much better here with this.
Okay, and do you know anything about performance per hardware between these two models? Is this model, for example, faster than used?
I don't know about the Midjourney, because like it's not open source, like they're running on their own servers. For this, just for inference, even with ControlNet, I think you are fine running it on 8 GPU graphics card. For training or for larger, because like the resolution changes the amount of memory you have to use. So if you want to generate it in 24, because there are other models like the fine tunings of Stable Diffusion or other models, just not so popular. that can generate natively at 1024, right? So you can use this and try generating at 2048 or something like that. It will cost you, like, it requires you a lot of GPU memory. But for just a naive implementation, 512 by 512 or 768, you're fine with 8 gigabytes GPU card. Oh, yeah.
You have mathematical degree for what you added for programmer the mathematical formula and first partition of your presentation.
Yeah.
It's not correct.
Which
You
one?
have done it.
This one? Yeah.
What does mean this one? This one. You know what it means?
It's the norm, L2 norm.
Normal. This one.
L2
This
norm.
one. And previous. It's not correct.
It is correct.
You added mathematical formula. You must correctly.
I mean, you must speak to the authors of the paper and reviewers in the conference where the paper was published. I mean, it is. But yeah, of course.
All programmers, but this mathematician is not correctly.
Can you name what's incorrect here? But what's incorrect?
Must be what is mean? This square 1 minus what is alpha t?
The amount of noise added to the image, like the scale.
What noise?
It's a scale.
Noise. White noise.
White noise? That's the idea here.
Noise is
Gaussian noise.
many things.
Gaussian noise sampled from the Gaussian normal distribution, zero mean unit variance. Definitely. But it's machine learning we have, like.
You must correctly mathematician.
But I mean, oh, I'm completely not a mathematician, but you must understand that this authors of the paper created this equation, and this paper was peer-reviewed in the conference. So I certainly that this is correct. Any other question?
There was actually one question from behind, but a person was missing until now. Here you are.
Oh, yes. Oh, thank you. I was just considering, because it's a lot of topic for the newbie. I was interested if you could share all the resources at the end of the slide that you had that I missed. Is it possible to share it on the Meetup website or?
Sure. Yeah. I will even add a few more links here. So
thank
yeah.
you.
Sure. So that's it. I think we can conclude. Thank you. Thank you very much.
Okay, so once again, thank you. And now, well, it's not gonna be a break. We'll just continue. And now, Maciek Aleksandrowicz is going to talk about what's going on right now in robotics, what was shown on the ICRAD 2023 conference, which is the biggest conference in the world in terms of robotics. It's IEEE Robotics and Automation Conference. Well, it's a big deal. And Maciek is going to show us in a second what was there, what was like, what is the current state of the art in robotics. So give him a round of applause and just like wait 2 minutes before he's gonna set up his computer. Okay, so run for a beer. You got the time. Okay, so we're all set up, and let's start with an applause for Maciek. And as I said before, it's all gonna be about the state of the art of robotics in 2023. So Maciek, the scene is yours.
Thank you, Krzysztof. Greetings, everyone. As Krzysztof said, I will try to take some summary from the trip to the London, to the ICRA 2023. What is ICRA? It will be in a moment. But before we start, one thing to clarify. We have in a schedule about 30 minutes. It's almost impossible to compress 5 days of conference in 30 minutes. So I decided to do some trickery with our plan. I will try to highlight things which will be not available in the internet. By that, I mean we do a photo relation from laboratory tours to the University of College of London and University of Queen Maria of London and to their robotics laboratories to highlight what the England is currently doing in terms of our favorite topic. All right. A brief remember who I am, as I was announced. My name is Maciej Sodrowicz. Maybe you remember me from the second meetup when I was talking about behavior choice. I'm still a PhD student at IGH University, and I'm still doing that little research thing with deep reinforcement learning for robotics. And as you can assume, if you want to connect with me, just write up to the Craig to our meetups, and somehow I will receive the message. Before we start, one thing which actually probably Maciej from the first presentation actually clarified it. When we're talking about things in robotics or the projects in robotics, we can divide it into separate fields. First, the problem of manipulation, when we try to grab something and manipulate that object in our scene. And that's the first one. And the second one is to grab ourselves and move around. And that problem is called navigation. Everything what will be today showed as from that photo relation will be somehow related to these two main problems. Even you can connect these problems if you put the manipulator arm on the moving robot and you have two problems to solve. A very tricky thing to do. Okay, when we're talking about robotic conferences, if you want to go somewhere where it actually is a big audience and a big persons from the field, we can talk about three main conferences. The ROSCON, which stands for Robotic Operating System Developer Conference, ICRA, which is International Conference on Robotics and Automation, and only IROS help us in decrypting what actually it means. ICRA is International Conference on Intelligent Robot and Systems. Three, the largest conferences on robotics, and you can debate which is the best organized, which is the one we want to get. However, today we only focus on the ICRA, which already happened. And ICRA, in the ICRA, which happened about a month ago, from the beginning of the ending of May and beginning of June, was about how to connect robots with human scientists. It's a very niche topic. The main topic of the conference was that. What the conference was split in so many ways and so many groups that you can easily forget that there was a main idea, and that's why there was some artists who are trying to connect with robots, or maybe there was some persons from the art and not properly science. And what ICRA 2023 is actually. First, it was a scientific conference. Thousands of scientists from all over the world was talking about the research. And the research, actually, which Krzysiek mentioned that I will describe, will be not described in the presentation. And that's probably why I have this brochure from the conference. here are the poster sessions, all topics from the conference. There are over 100, almost 200, over 100 topics which was covered, from the medical robotics to all kinds of manipulation. When you want to grasp cabbage, there was a robot to grasping cabbage. If you want to navigate in radioactive environment, there was a robot for that. The works were all over the place. And if you want to describe it, well, actually, you can do it by yourself by Googling the ICRA 2023. It's not fun to describe something which already you can do. So what else ICRA can offer us? Industrial exhibition. It was a nice place when the academic society can coexist with industrial ones, where every company who had something to talk about robotics, maybe to just present the ideas of software or just their new hardware platform, was over there. If you want to see a Boston Dynamics with their spots, they were. If you want to see more local sponsor like Husarion also went there. There were tons of maybe not tons, but dozens of many companies like maybe Dyson or iRobot or John Deere, everyone who wants to maybe not sell, but to present something relating to robotics. And the last one, what was actually interesting, it was our robotic competition. Parallel with all two main things happening at ICRA, there was also 5 days of robotic competitions in 13 disciplines. Here is an example of Cracow Group, Kołnaukowe Integra, ambitious students who tried to achieve something in a competition with F1 1TEF, where the task is to have an autonomous, a small car which tries to race in with other cars in a race in desired environment. As I said, there was multiple robotic competitions, and I must highlight something here. Some of the competitions were simulated, like simulated humanoid robot wrestling competition, or there was another competition with manipulation, virtual manipulation challenge, bin picking, assembly, and stacking. And by that means, some of the organizers of that robotic competitions are keen on to continue that idea. Even if you don't have a robot, but you have if you want to play with something like idea of algorithm or maybe you approach to solve a problem, you can start sending by GitHub or other repository means your solutions and start to competing with others. Even if you can't go to the competition, go to the conference itself because it's very expensive to go over the world, you can still achieve something and say that you were part of that conference. And by that, let's summarize the main conference by 3 slides and the 3 main guests who were invited to the whole conference. The conference actually was for 3 main days, and there was additional 2 days on Monday and Friday for extra workshops or the laboratory tours. That extra days are actually worth mentioning because as far as I know, it will be not available to the public. But plenary sessions. Plenary sessions was held in auditorium. When you were sitting there, you were thinking you are part of maybe launching a new product. Maybe you heard our presentations from Apple or AMD or Intel when the CEO is standing on scene. There's a large monitors and they're talking about a new product really wants to sell you in a couple of months later. Here there was a very similar environment where hundreds of people are sitting, and on the scene there were some guests. Guests are all from the academia and industry, just to talk about something like a TEDx, but just for that audience. And on the first day, as I remember, it was Tuesday. A guest who was invited was Mr. Hacker. If someone here is related to not bioengineering, that kind of engineering which involves some medicine, you probably heard about him because that guy lost his legs during his 20s, and a medical doctor told him he couldn't go back to the climbing. And he was thinking, if the technology is evolving faster than human, maybe he could help the technology to evolve and overcome his problem. So he started learning math, physics, IT technology, and after a couple of years, he started developing his own program on bionic limbs. And he was talking about all the spectrum of research which he is already doing in that field. What is important to highlight here, that bionic limbs have a feedback. As in some means you have not a full haptic feedback, not full proprioceptive feedback, but some kind of feedback which allows you to move around freer than just a damp material which you can't feel but somehow is applying to your moves. Then on the next day there was another guest, Miss Yasia Reithart. I was pretty confused how to pronounce her name until I googled her, and it happens that she is from Poland. She was born in Warsaw in 1933. She is a historian in England, and she is the person who coined the term uncanny valley. If someone heard about it, probably in terms of CGI, movies, or maybe art science, we can thank her for bringing the research from the Asian professors, Asian doctors, to more Western world by that term. If someone doesn't know what is uncanny valley, it's a thing when a robot or maybe just animation of a humanoid looks like a human, but you are starting to perceive it like it was something is going on, like it's not very good human, like it's a mistake that doll or something artificial is trying to speak with you, like something is going on. Maybe you watch a very old movie like Polar Express, where there's a problem with mimic on the faces, and due to the fact that all the animation of the faces was doing very poorly, some people started to feel uncanny. That's the name of that uncanny valley. When we're starting to model anthropomorphic robots, it start to look cute, maybe some funny, maybe like good. It was in Poland. There was some time ago. There was a Carrefour robot from the Carrefour. He looks cute because he had some cat ears, and he was talking like, please don't touch my ears, something like that. People love them, but imagine if you started to give that robot more a human face, like a little girl or something like that, and you will reach a point when that face will be very, very, very stiff, very dead, and you will hear some voice and you will watch the face and something is going on, that something dead is speaking to me. You started feeling to very uncanny. And then if you properly starting to applying some art science to that, and the animation will more smoothly, everything starts to go fine. That was a little tutorial. I hope it will not cost us the whole presentation. And on the third day, there was another guy called Mark Rybert. He started his presentation with a very fun slide that he got two loves at first sight. First was the robot, and the second one was that girl. and he told the audience that the second love didn't last long, but the first one is still going on even today. And by that, he took a good choice, probably a lifetime choice. As some of you can recognize him, he started the leg laboratory, the very special laboratory which started the whole Boston Dynamics company after some time. And with that presentation, he was talking about what the new thing, the offspin of Boston Dynamics called AI Institute will do. In very short words, they want to research things like interaction of human and robot, or how robots should interact in human environment in perspective of algorithmics. That fields are not very simple. And as I took photo of that slide, Mr. Mark highlighted 4 areas, technical areas: the cognitive AI, athletic AI, advanced hardware, and ethics and policy. So they wanted to address that problem with a holistic approach. And what else with Mr. Mark? He also presented a couple of funny videos, the failure videos, the actually work which we are robotists are prone to do. When you are trying to record something and you fail, you probably don't publish that video anywhere, because what is fun in looking at a robot which fails? But actually they saved some takes from the advertisements of Spot, and there was a funny video where Spot is trying to give the can and like a dog which is very stubborn to take the can and with self. And which I don't have a very good recording of it. They tried to make some dancing of the spots. Spots have to dance to some old waltz and pass the rows between them. However, after a minute, they somehow pushed ourselves and laid dead. Okay, that was my take on the plenary sessions. As I said, I will not cover the poster or other things because we don't have time for that. But we will dive into the laboratory tour, and the first one inside the walls of Queen Mary University of London. There was a Center of Advanced Robotics. If you have any question regarding that, please hesitate till the end. I will try to help you find more resources about the things which I will present, because I really don't know much about them. First, entering their laboratories, a very fancy conference room, which actually is a classroom for students. After some briefing, we went to the first station, the first experiment which they were investigating, the teleoperation, very important, for instance, for atomic organizations like in England. They need to decommission many of reactors or experiments related to radioactivity. So somehow the operator, which is standing here with some haptic device, needs to feel what robot actually feels on the other side. Seeing like happy operator is trying to grab something, we should focus on the robot itself, because if you consider this 4-finger gripper, there are many sensors, and the experiment itself is to how to grab something and to send that haptic feeling to the operator. However, we can say it's still at the beginning. If we consider that someone wants to push the object with that side of the fingers, there are no sensors at all. There are some pipes or cables So there are still lots of work to do if you consider intuitive approach from the human. Moving forward, the experiment with virtual reality. The operator here, the researcher, was talking about how to prepare a reliable virtual reality interface to control the robots. And what a surprise! Actually, it was not a surprise. He told us the first approach was to track the motion controller and move the robot accordingly to the motion controller. That approach have a very little problem. If by some means the controller was out of the scene or due to some malfunction, the sensors lost the information where the controller is, the simulation probably will send that controller in virtual reality to the point of origin to 0, 0, 0 or something like that. And the robot which is tracking the controller will immediately start moving to that position, which wasn't very safe, especially when you're trying to do something very gentle and related to human. So they decided and insisted to start to replicate something like Arvis, that with Move It plugin, that with that controllers you can grab a position, decided position, and move it somewhere. Then when you are when you can ensure that that target position is good enough, we can plan the trajectory and send the robot to that position. What is not seen here, it will be another moment, is the scene of the robot. Here there was a little disruption. They was showing us their sensor, which couldn't use any electronic parts at the tip. They just started monitoring some light and measuring the light. They're starting mapping how much light they are receiving on the sensor in terms of touching something. For that VR experiment, there was that scene with a soft deformable object, which was just a teddy bear, plush teddy bear, and two Kinect, Xbox Kinect cameras to obtain some cloud points, how to navigate in terms of virtual reality. Moving forward to next station, which was presented. Anybody here heard about soft grippers? One person, second, they actually some persons here. The soft grippers are actually very fancy because they don't need electrical parts to be controlled. Actually, by what I mean by the place of operation, of course, they are mainly using pneumatics. And they don't need any kind of force feedback because we are leveraging the problem of grabbing something gently to the mechanics of the soft gripper itself. Here are idea of that researchers to model 3 arms of octopus to form a simple gripper. And they got an interesting approach, even if they got a very old, and maybe we can say, robot arm, which would be currently used in Polish university. They wanted to present the invention of gripper. And here they was gripping just above. It was a pre-recorded demo. Very funny that the guy behind that experiment couldn't be there, so he prepared a video clip with himself talking about the experiment, and the experiment was programmed to do it all by itself. If you see here by position that the gripper actually grabbed that ball and moved it to the top. Here you can see the lines of the ball that is facing over here. The whole idea that you can grasp something and move that way was you can rotate it. If you can see that lines of the ball, it was moved by some degree, and it was grasped again. What it means? It means that without any auxiliary position or robot or arm, it was possible to manipulate the object, which was still grasped, and it can be placed again in the original position. There are probably some applications which could benefit from that. Moving forward, a little bit moving to the endoscopy or maybe to the field of foldable robotics. If you consider that you make a robot from anything which moves, why do not make a robot from a plastic foil or other kinds of foil which can be inflated and deflated? And that was the idea how to create a gripper which on the beginning is folded. But that means it takes very little space. It can be inflated with air, and it unfolds to such shape, which further can be, of course, inflated again into other chamber and grasp something. Very intriguing, and thanks for applying for that application in soft robotics. Moving forward to another station, probably just to sightseeing of that laboratory. If it was important to me to take that photo because we have here 1, 2, 3, 4, 5, 6 behind the hair, 7, 8, probably even more 3D printers, which isn't a very common view in still in Cracow universities. If you have one 3D printer, that laboratory is very good, in very good condition. But here we have 8, and I was considering, maybe I will take the photo, I will show to the highest persons in the university that maybe they want to buy something to be at least less as that university in England. Say it again.
High schools have more. My brother is a teacher in high school. They have 3
Oh my goodness. 3 printers in high school. Actually, I can believe in that. Even in my technical high school, they were 1 or maybe 2 printers when I was ending the middle high school and going to my studies. There was actually 2 3D printers already, both with tons of Lego Mindstorms and other things to teach robotics in technical school. On the university, on the other hand, there was a problem with everything, but that's a digression. Here is an interesting thing for everyone who is working with drones, with quadrocopters especially, because mad guys told us they have an idea. They wanted to create a quadrocopter which is solely powered on solar power. So they just show us a little video. That's why you are seeing a screen with a screen on it, where there's a very small waffle and that small cross, that brown cross, it's just the solar panels from the bottom. And they was talking about the motors are powered from the solar, and for electronics and stability, there are also, of course, some batteries just to start up everything from the ground. Moving forward, here we have an interesting piece of hardware. When you are trying to research such things like soft robotics or how to grasp something, you want to have information how humans grasp something, like a cube. Probably a cube which can be can have a change in mass. It can be open-end and different mass can be put inside. If you have a very good eye, you can see a laptop with some terminals. Actually, that cube is running on ROS1, And by that, the researcher who developed it actually showed us how how can be visualized in RVs. How it work? How does it work? These little transparency, not cubes, what it's squares, are made of silicon and have a little magnet inside of them. Under them, there are some Hall sensors which are constantly monitoring the magnetic field, and every change in the magnetic field it will be probably related to change in position of that magnet. And as you can imagine, there are some problems. Like if the cube is sitting on the table, you have to consider that the magnets from the below are already pressed by the mass of the cube. Or if you are moving around the Earth with that cube, the magnetic field of the Earth is actually measured by that little Hall sensors. All these things had to be calibrated, and even the creator of that said he didn't consider things like taking the characteristics of the sensor and developing another one batch of that sensors, because it's so much tedious work. He wants to do his experiments in that setup and move forward probably to another iteration, not to looking behind of it. Here he is touching a palm of that cube, and on RVs it's pretty well visualized. Moving forward, actually take from his paper. And here a little session about, again, soft but pneumatic robotics. As you can imagine, there are some places in the world where human shouldn't enter, and even robot shouldn't enter. And by robot, we means that robot which can ignite something by using electronics. So maybe that electronic could fail, like in wells when you want when you are producing flour for probably baking a bread or maybe some cakes, or maybe in radioactive environments like investigating fusion reactors or atomic cores. You can't go with robot electronics because that electronic will fry up. So what you can do? You can still do something with mechanical things, like that stomper robot, which by using adequate control of inflation and deflation of that springs, it can move around. Another example of that is a gripper, again without controllers. Actually, of course, some there is actually an electronic controller which controls the pumps, but it's not necessarily placed inside the gripper. And here was the idea how to create a gripper for that bottle. And yes, for fast prototyping, they used a surgeon just to do some experiments how it folds and unfolds due to some external pressure. And they're of course using Arduino because it's very fast to connect some external sensors just to measure how it's working currently in the proof of concept state. Moving forward. Here another idea of nature-inspired gripper based on octopus with the logo of the university. An interesting approach to tactical sensor. Here we have a sensor which will measure how much force is placed among it. However, it doesn't work in conventional ways. Actually, that little wires around it are optic fibers, which brings the light, and under it there are some camera. That camera is monitoring the intensity of light, which further can be interpreted by some means of force applied to that surface. Moving forward, a very simple example of exoskeleton. Here, just the glove. That thing which looks like a driller is just a electronic pneumatic pump, which can give some external air pressure, which is connected to that foils around the hand, which allows to grasp something with more force. Very interesting terms of research in helping old people to recover from something. And what else? The last thing in the Queen Mary University of London was that cage with drones and their research, how to denoise audio from the motors, which if you ever hear the drone which is flying, it's not a pleasure sound. It's very loud. It's very hard to start talking with other persons. And they actually wanted to have some voice commands for that robot. So they created an array of microphones and they tried to model somehow how to cut off motors from the input noise. Yeah, I remember about timing. As you can see, we are in half, so I will try to move forward as fast as I can. The University College of London, they had they had two laboratories actually. First was the mobile robotics, where you can see a unitary one, which actually was broken by the other group. Experiment of grasping and determining the orientation of screwdriver, and another experiment of manipulation where they just wanted to grasp some cabbage, and to train that robot they got some styrofoam foam objects to train it in means of reality work, and then they bought some vegetables just to consider how well it's working. Then moving forward, there was a small area, looks like a playground. If you fill with balls, it could be also used for children instead of robots. Lots of robots are over there standing here. We don't have time to show the very nice video how that little robot dog wants to get back on its knees, but it's starting learning from very scratch, and it talks about an hour of training, of trying an error to learn how to get back on their legs. And another experiment with another unitary robot. Is there a possibility to model a very low controller which can be robust in terms of distribution, like a very bad human with a long stick, which will be used to push the robot around, and the robot will try to maintain its position. There was another one with the line which human wants to pull the robot. But let's focus on that very simple example of navigation problem, probably just to teach the scientists how to work with spot in very foamy environment. Before we move forward, as you can see, they got a lot of cameras. The whole laboratory was actually monitored in terms of position of our robots. If there was another external plugin, it was also possible to gain some point cloud of the whole compartment. It was blowing my mind in terms of costs to maintain that hardware and software. They show us one startup from there. They created devices for ultrasonic levitation, or actually for ultrasonic haptic devices, which also can be used for levitation. Here are some just screenshots. It's very hard to show the feeling of touching, so just little speakers with palm of it. And moving forward, again, don't have a time for showing ultrasonic levitation experiment. Maybe during the questions we will see. Sorry for that. Another perk from them is that they can use only one part of speakers to levitate a little object in the air. And the last part of our tour was in the another building. Actually, it was the department of architecture, of robotics, and bioengineering. It was very interesting to hear about collaboration with that three disciplines. First, as you can imagine, that drone over here was used to build something with foam by layers, a multi-agent problem where multiple robots are trying to deliver building material in right order in the right time. Here was the whole concept because they want probably to build one building with that. I didn't have time to digest in all the materials which they have provided. And these robots was the one part of that laboratory tour, and the second part was the huge industry hall with a very huge robot. It was taking all the attention from the group. What that robot will be in a moment. A guy here was talking about how the industrial robots are used to teach the architecture students to the new ways to connect materials to achieve new arches or new roofs or walls. Here was the stack of software and hardware. Here there are some screenshots how they were developing ways to develop new shapes for buildings. And I'm moving forward till we enter interesting idea that they took the department of bioengineering to develop new materials, new eco-friendly materials which can be used for building, for instance, for growing some food on the wall. And they achieve it in terms of printing with robots, not with the 3D printer. They also research if there's possibility to recreate traditional, very old methods of building, like from 1,000 years ago, by using robots. And yes, they accomplished that with very low-cost materials from actually the wood, which can be formed and dried to achieve stiffness. And what else we got here? The actual pair of the whole trap. The guy over there was describing the vision system. The vision system consists of multiple cameras on the ceiling and on the ground level. They was talking about how they calibrate that system with that little laser thing over there, which have accuracy about some micrometers. They put around laboratory stand multiple of these things, which originally have a place for a mirror to calibrate it in terms of micrometers, and then they have a little marker which can be observed through many cameras. They rely on fact that probably the ground floor will be not moving because it's connected through foundation to the bedrock of that place where the building is standing. And they told us by the multiple camera setup, they achieved information that when that part which was investigated was cooled in terms of cooled air, through cameras, they could register the change of shape of the metal in about 40 micrometers. It shocked everyone, and probably it's not a surprise they took about a decade to develop the whole system and calibrate it, and many master theses and doctor theses were developed under these circumstances. Alrighty, it's probably the last slide. The company behind that creeper with that snaky thing is defunded, but the thing is still going on. And what else? Probably that's all. And yes, do you have any questions? There is a question. Maybe a microphone. Maybe I will give him our.
Okay, after this experience, have your plans for the future changed? Because it looks like a mind-changing conference.
Okay, very interesting question. Actually, I verified that the ideas for my PhD research should be more novel, even if I hear that the novelty is good enough. But it opened my eyes that probably we need to make more steps at one time to research things which are actually researched in the West. Another question. Short one.
I know everybody wants to go home. After we've seen the state of the robotics current in the world, because it was international conference, do you think that the promises of our beloved tech Jesus Elon Musk about the Tesla robot are actually in any way actually like realizable? Like they are you can make a a humanoid a robot that can be affordable for everybody, and again I quote that can be twice as much robots as humans on this planet. Is it even possible? What do you think?
All right. An interesting question. How can I say it? Seeing the state of the art at current level and how it's developing year by year, that level which Elon Musk is promising us probably will be available at the end of current century. Probably. 2 years. Like the autonomous cars are just 2 years since, or 10 years since, almost 10 years since, I forget when. Like in Poland, we have our problem. We are saying we will have an atomic power plant in 10 years since 1960s. It's 10 years cycle. It's a still long road to achieve such promises of Elon Musk. All right. If there are no more questions, I thank you all for your attention, and especially that we have almost ended our time for meeting. Thank you. Now I will pass the microphone to Krzysiek to end our meeting.
So yeah, thank you everyone for coming here. It was another great meetup, I hope. Like, it's up to you to judge. And we will have a survey for you to fill if you feel like it. Like, if you feel like it, to fill it. Well, that was not planned, by the way. So yeah, not this one. In a moment, there will be a QR code. Oh yeah, here it is. If you feel like, you can just give us feedback on how we do, like what would you like us to change, etc. And obviously rate us. So we can keep on improving. We can just like those tiny little things that bug you that maybe we are not aware of. Anyway, this meetup is the last, but in this season. So right now for summer we're gonna stop, and the next meetup will be somewhere around October. Like after summer, so you don't have to worry that, oh no, I'm gonna be on a vacation and there is a meetup and I can't be there. Like I'm pretty sure that's what you're afraid of. So yeah, we keep it in mind. And yeah, once again, thank you very much for coming. And right now, we have a networking session. So grab yet another beer and have a nice chat with each other.